What the heck?
Tagon.
So how might we go about this? The first step is to simply take the derivative of both sides. These are all we're just going to assume that these are all completely differentiable. Keep in mind that r is a function of x and theta is a function of x. So these things depend on x. We're taking the derivative of everything with respect to x. Okay? So we're assuming that r and theta are functions of x. We're going to prove that theta is in fact x and that r is just the constant function 1. And that's all we have to do. So let's take the derivative of both sides with respect to x. If you take the derivative of e to the power of something, you keep e to the power of something because the derivative of the exponential function is itself. So we have e to the ix. And then by the chain rule, we simply take the derivative of the inner function. The inner function I times x, if you take the derivative of something times x, you just get the constant. That's just following from the power rule. And the constant being multiplied onto x is I, the square root of -1. And now we have one function of x, namely the radius r, times some other function of x, which is theta, right? Theta and r are a function of x, so I want that to be clear. So because we have a product of functions, we have to use the product rule. So the product rule is very simple. It's simply the derivative of the first function times the second function plus the first function times the derivative of the second function. I may end up doing a video where I prove these derivative rules for functions. If I do, then that's when the justification will be found for this, but it's just the basic product rule in calculus. So it's the derivative of the first thing, which I will write as dr dx, because again, r is a function of x, times the second function, which is just this entire parenthetical part, cosine of theta plus I times the sine of theta. And then we add the first function times the derivative of the second function. So adding r plus the derivative times the derivative of the inner function. Now the derivative of the cosine of theta with respect to x is negative sine of theta times the derivative of theta with respect to x. This is the chain rule because, as I said, theta is a function of x. So the derivative of the cosine of something is the negative sine of that thing. And now we have to multiply by the derivative of the inner function, which is theta, as a function of x. So d theta dx. Right? And now we simply add the derivative of the next term, which is plus I times, what's the derivative of the sine of something? It's the cosine of that thing, right? And now again we have to multiply by the inner function, namely theta, which gives us d theta dx. Okay? And so we know that if we take the derivative of this function, as it's equal to some complex number using this representation, this is the relationship that we get. But notice that the derivative of this function is just I times the original number. So we can actually say that this is equal to I times cosine of theta plus I sine of theta. Because look, it's just I times e to the ix, and we already assumed that e to the ix was equal to this complex number representation. So we can simply replace the e to the ix with what we said it was equal to, which is why it now says I times r times cosine of theta plus I sine of theta. The cool thing about complex numbers is they are only equal if their real parts are equal and their imaginary parts are equal. So we can sort of FOIL these two things out, combine real and imaginary parts, and then set those things equal to each other, because that's the only way that one complex number can be equal to another. So what I'm going to do is I'm going to set this and this equal to each other and do just that. So now we know that I times r times the cosine of theta plus I sine theta is equal to, what did we have? We had dr dx times cosine theta plus I sine theta plus r, and I'm going to factor out d theta dx because it was in both terms, so r times d theta dx times the derivative of the inside, which was negative sine theta plus I cosine theta. So this is what we were able to prove, that these things are equal. And now what we're simply going to do is we're going to distribute the terms in, collect all of the real parts together, and collect all the imaginary parts together. So if I distribute this IR into this, we'll end up with negative R sine theta plus IR cosine theta. And if I collect all the real parts of this, I'll end up with negative R sine theta times d theta dx plus dr dx times cosine of theta plus I times, now what are all the imaginary parts? We're going to get r d theta dx cosine theta, so r cosine theta d theta dx plus sine theta times dr dx. So I'll write it as dr dx sine of theta. Okay, and that's all. I managed to fit it all. Okay, so now what we have is that this complex number is equal to this whole complex number here, which is really great. And what we're going to do is simply take a look at the real portions. This real part has to be equal to this real part, and this imaginary part has to be equal to this imaginary part. But you'll find that if you do this with the imaginary part, you'll get the same answer in the end. So I'm just going to compare the real parts. You only need to do one of them, and you'll see that we get the answer that we want. So if you feel the need to prove it to yourself that working with the imaginary parts yields the same answer, then be my guest. We're simply going to compare the real parts. So we know that because this complex number, which was I times e to the ix, right, is equal to this complex number, we can simply set the real parts equal to each other. So what do we have? We have that negative r times the sine of theta is equal to negative r times the sine of theta d theta dx plus dr dx cosine of theta. And what we notice right away is that we have negative r sine theta here, and we have negative r sine theta here. And what we don't have is a cosine term on this side of the equation. Since there is no cosine term on this side of the equation, yet these two things must be equal, then somehow this cosine term has to be gone. It has to be equal to 0. Well, I understand that you can pick theta to be anything you want, and cosine is only 0 at odd multiples of pi over 2. So the only thing that could be 0 all the time to ensure that there is in fact no cosine term is the derivative of the radius with respect to x. So we know that dr dx must be equal to 0. But if the derivative of something with respect to x is equal to 0, that must mean that the function r must be a constant with respect to 0. So this implies that the function r is equal to some constant, c, that is in the real numbers. So we know that r is equal to some constant, and that constant exists in the real numbers, right? Because the radius is by definition a real number. So what that tells us is that this term actually goes away. We don't need it. That's equal to 0. In fact, I can erase it. So we have this fact now, and we can sort of set that aside. The cool thing now is that we only have these negative r sine of theta terms, but one of them is multiplied by d theta dx. Now, the only way to multiply by something and not change it and end up with this thing that you were multiplying it by is for that thing to be equal to 1. So we know that d theta dx, or the derivative of the angle with respect to the input x, it has to be equal to 1. And if we integrate, so we end up with theta as a function of x, we must see that theta is equal to x plus some constant, because the derivative of x plus a constant is 1. The derivative of a constant is 0, and the derivative of x is just 1. So for more clarity, I'll label the constant that r is equal to be c1, and the constant that is being added to x when we evaluate what theta is, we'll call it c2. And c2 is also in r. So c2 is also in r, as in the real numbers, right? Now, what did we want to prove? We wanted to prove that r was equal to 1. We somehow have to prove that c1 is equal to 1. And we want to prove that theta is equal to x. So we somehow have to prove that c2 is actually equal to 0. Right? Because then if this is equal to 0, it's just x plus 0, which is x. So we have these two very, very important facts that we have now. And I'm going to erase everything that we've just done and sort of close this little proof now. So we started from the fact that e to the ix must equal some complex number, which can be represented in this way, as some number that lies on the unit circle times some distance from the unit circle, which is a scalar multiple, so that you could make it as large or as small as you want. And we want to show that r equals 1 and theta equals x. And so far what we have is that r is equal to some constant, c1, where c1 is a real number, and we've shown that theta is equal to x plus some constant c2, where c2 is also a real number. Now, how do we prove that c1 is 1 and that c2 is 0? Well, we can consider a base case. We can consider something that we know e to the ix has to be based on exponential rules. Let's just see what happens when we take x to be 0. If we take x, so we're going to let x equal 0. Well, we know that when we do that, we get e to the I times 0, not theta, e to the I times 0, which is the same thing as e to the 0, which, almost by definition of how exponents work, is equal to 1. But 1 as a complex number is the same thing as 1 plus 0i, which is to say that it lies on the real axis, on the unit circle. So this is the unit circle, and this is the point 1. This is the real axis, right? And this up here is the imaginary axis. And so this is the point we're looking at, this point right here. But if we consider this point, what is the radius of this point? The r value. It's 1. The distance from 0 to the point 1 is 1, which means that the radius of the number, e to the I 0, is 1. But we know that r is equal to a constant for every input of x involved in this function, which is to say that if it's 1 for a single point, it's 1 for all points. So you may notice a color change all of a sudden. My camera actually died, so I had to change the battery. So what was I saying? Yes, we just determined that because the radius is 1, or r equals 1 for this single input, 0 for x, that because r is a constant, it must always be 1. So we've actually proven the first thing that we wanted to show, that r is in fact equal to 1. So we know now that r equals 1. Cool. That's the first step, right? We wanted to prove that the radius of this number, the distance from the origin, is in fact 1. So now we can remove r, because we know that it's just equal to 1. And we can erase the parentheses because we no longer need to multiply by something. And now all that's left is to show that this constant that's being added to theta is actually 0, which means that theta does equal x. And that's not too hard to show, because consider what is this angle of the number 1. By the way, this is the real axis and this is the imaginary axis. But if this is pointing strictly in the positive real direction, that must mean that theta here is 0 radians, right? Because this is the definition of what of 0 radians is, when you're pointing in the positive real direction without having turned any multiples of 2 pi. And what did we plug in for x? We plugged in 0 for x, so we know that x equals 0, and it's equal to, what angle do we have here? The angle is 0, right? It's on the positive real axis, so the angle is actually 0 plus some constant c2. But if we have 0 equals 0 plus a constant c2, what must c2 be equal to? c2 has to equal 0, which tells us that x is not just theta plus some constant, x equals theta plus 0, which is to say that x equals theta. So we have proven both of the facts that we wanted to show, and now we can simply replace theta in our formula with x, and we have demonstrated exactly what it is that we wanted to show. That Euler's formula is in fact true. That if you take the base of the natural logarithm and raise it to the power of I times x, we get the cosine of that same x plus I times the sine of that same x, which is, again, to say that e to the ix is any point, where this is the angle, by the way, is any point on the unit circle, given some angle around the unit circle. X is that angle, which is just absolutely lovely. That is if you pick that x is a real number. You can of course put any number you want into this, and we'd have to figure out what cosine and sine of non-real numbers are, perfectly well defined. This is actually going to be the way that we can figure that out. We've proven what we wanted to prove. I'm going to use the fact that we just proved this to sort of introduce what we're going to be doing in the next lesson. So now that we've demonstrated Euler's formula, so I've had to get another color because those pens are running out. So we've proven that e to the ix is equal to the cosine of x plus I times the sine of x. Okay, so now that we've shown this, in the next video I'm going to be doing some manipulations of this formula by plugging in a different version of x, namely negative x, and then using the odd and even aspects of the sine and cosine function to sort of get the different ways of representing them. And we're actually going to use that to solve for cosine of x and sine of x in terms of this complex exponential form, which will allow us to introduce two new functions, the hyperbolic sine and the hyperbolic cosine, which is what a few commenters have asked me to do. That will be the next video. This video is already running long enough. We're also going to use that to figure out what sine and cosine of complex values are. So actually, because this is true for any number, complex or otherwise, what I'm going to do is actually replace the x with z, because from now on, we're talking about complex numbers. This is where z equals x plus I times y, and x and y are both elements of the real numbers. The imaginary part is y and the real part is x. Both of those are real numbers. So I hope this was really interesting. I hope you got a lot out of this. It's a beautiful, beautiful formula. It's one of my favorites. Oh, and real quick, before we go, let's actually pick a specific value of z. Let's pick pi, right? So we have e to the I times pi, the exact number e to the power of the square root of -1 times the exact number pi, pretty ridiculous combination, equals the cosine of pi plus I times the sine of pi. Well, what is the sine of pi? The sine of pi is the y-coordinate of the point that is pi radians around the unit circle. Well, pi radians is pointing in the exact negative direction in the x-axis, and so that means it's not up or down, which means the sine of pi is 0, which means this is just equal to the cosine of pi, right? The I doesn't matter, right? But what's the cosine of pi? It's the x-coordinate of that direction. And because we're on the unit circle pointing in the exact negative direction, this must be -1, which is to say that Euler's identity, the beautiful formula, e to the I pi equals -1, exactly, which is absolutely ridiculous. An even more lovely way of saying it is to simply add the -1 over. So we have e to the I pi plus 1 is equal to 0. And we have just about everything you could ever want in one amazing formula that I couldn't possibly tell you, like, how the universe was able to make this happen. Like 3 different things that were independently discovered in like 3 different subjects: geometry, solving algebraic equations, and economics, or the study of growth of things, the multiplicative identity, the additive identity, equality and addition, all together in one beautiful little formula. And it's absolutely stunning. One of my friends from college, who is also a math major and is currently doing graduate school, has this tattooed on his arm because it's just stunning. It's absolutely beautiful. We will continue the study of this formula, seeing where it goes when we try to figure out what cosine and sine are in terms of complex exponentials. That's all for now. Thank you very much for watching. I have an Instagram page for the channel. It is at what the hectagon, of course, spelled correctly, unlike my email, right? Hectagon, I spelled in the email with an A here when in fact it's an O. What the hectagon on Instagram. So this is Instagram. I post channel updates there. I also am doing a lot more reading than I used to now, so I'm posting books that I'm reading that I recommend to people. I have a collection of vinyl records that I like to share. Follow me at what the hectagon on Instagram. I'd like to point out that one of my best friends, who is very much into Dungeons & Dragons, has a YouTube channel called Marching West. He does like a little podcast about Dungeons & Dragons. He does Dungeons & Dragons all the time through his Discord server. He's very, very into it, and I'm sure he would appreciate a bit of a mention. So if you're into Dungeons & Dragons, visit his YouTube channel, Marching West. He also has an Instagram account, again, at Marching West. Also, this fellow, Bill, and I are starting another YouTube channel. I guess you could call it personal reasons, even though it's just kind of funny. Is called Fredwood Live. On YouTube, we're just called Fredwood. It's an amalgamation of 2 different things that were sort of important to us in our college days, which are getting farther and farther behind us. So this is, again, YouTube. We have a channel called Fredwood. We're going to do kind of silly, just us riffing off of each other vlogs that we edit together in humorous ways. But we're also going to start doing weekly video game streams on Mixer. And on Mixer, our name is Fredwood Live. So if you want to see 2 kind of dopey former college students do kind of ridiculous video game streams and also other things that we're going to do on top of that on Mixer, our username is Fredwood Live, so check us out. Likewise, we have a Twitter account to promote it, also at Fredwood Live. So I apologize for all of these different promotions. I figured I'd just start putting these out there. So there's a few that I'd like you to check out if you're interested. Is my Instagram account, What the Hectagon. On YouTube, my buddy Bill's channel, Marching West. It has to do with podcasts and the like relating to Dungeons & Dragons. The Instagram account for channel updates for that channel. Our joint channel, Fredwood, where we're going to be posting stream clips and vlogs that we make, which are not in any way intended to be serious. It's all supposed to be just kind of humorous. We're going to stream on Mixer because that's the only way that we can use the camera that we have on my Xbox One, and we're not about to buy a Kinect to do on Twitch. So Mixer, Fredwood Live, and the Twitter account for that is at Fredwood Live. So if you're interested in any of these things, please give us a follow. I really appreciate it.